Hello and welcome everybody to our new webcast, Basics and Applications in Spectroscopy. My name is Martin Labus. I'm from Laser 2000 GmbH. I'm a sales engineer for optical test and measurement, where our spectroscopy products and know-how is based. This is our agenda for today. So first of all, I will give a brief introduction about Laser 2000. After that, I will lead shortly into general aspects of spectroscopy. In the main part, I will go a little bit more into details for 3 specific spectroscopic applications and methods. And in the end, we will have a Q&A session. So whenever a question arises, please use the question function or the chat function on the control panel. We will try to cover all questions during the Q&A session. If there is a special spectroscopy topic that is not covered by this webcast, please feel free to either put your demand into the chat panel or just hit our website laser2000.de and leave us a note if you want to learn more about another spectroscopic technique. Then we can possibly make another webcast about some other parts of spectroscopy. Founded in 1986, Laser 2000 has more than 30 years of experience in all facets of photonics. We work together with manufacturers from all over the world to provide their products to our local customers. For this purpose, we have contact offices not only in Germany, but also in France, the Iberian Peninsulas, and Scandinavia. There are also partner companies in the UK and in the Benelux states. Our passionate experts and our wide portfolio enables us to create comprehensive solutions for every project, no matter how special. Our wide product range covers every kind of photonic product, from laser safety and optical components to fiber optics, and of course, solutions for optical test and measurement and spectroscopy. The term spectroscopy covers a variety of physical methods to study the interaction between matter and electromagnetic radiation, especially for optical spectroscopy. Spectroscopy enables us to observe changes in intensity and/or frequency, wavelengths, and so on. And with this information, one is able to detect, identify, and quantify information about atoms and molecules. With this information, it's able to derive some more physical or chemical properties. On the right side, you can see the typical emission line of a low pressure mercury lamp. But if you have a fluorescent tube lamp, you will see these lines as well. So all the spectroscopic methods covered by this presentation here work with a kind of dispersion of light. So there are many different ways to distinguish between the types of spectroscopy. One common type is to distinguish the methods of spectroscopy by the type of interaction that light has with the sample provided, like absorption, as you can see here. In this picture, this is the transmission spectrum of an optical filter, or emission, for example, like this emission here of a calibration light source with neon gas filling. There are also other types of interaction, like reflection and scattering. Another common way to distinguish between the methods is to divide between the wavelength ranges used. This can be, for example, ultraviolet, the visible range, or the infrared range. Of course, you can go even further into the red direction and use terahertz, or go more into the blue and go from the ultraviolet to X-ray. This is also possible, but nothing to be covered within our webcast. When we look at a basic spectroscopic setup or a spectrometer setup, there are three things that you always have to perform spectroscopic measurement. You need a light sample or a light source, so something that you want to disperse and detect. The second point is a dispersive element like a prism or a grating. And the third one is to have a detector, a screen, or like it was in the beginning, some kind of photoplate. For some types of spectroscopy, you can surely use the eye, but when it comes to laser spectroscopy, better go for a silicon detector or whatever detector, or for a photoplate. It's like 3 o'clock in the afternoon in Germany, time for Behrens' law. Unfortunately not. When talking about UV and visible spectroscopy, one is mostly confronted with absorption and transmission measurements, and these measurements make typically use of Behrens' law. So Behrens' law describes, so simplified, the optical attenuation of a material or a sample. But even though it's not Behrens' law, it's still great for making cocktails. This is our Laser 2000 brand cocktail, which was mixed on a Laser World of Photonics trade show. Unfortunately, in 2021, it will not take place, but please feel invited to contact us and participate, hopefully in April 2022. The basic setup for an absorption or transmission measurement consists of the following things. This is a broadband light source. Of course, a sample, unless you want to measure the light source itself. And of course, a spectrometer. And normally you take a reference measurement out of your broadband light source, maybe including the container your sample will be placed in. And then you take the sample measurement, and then you compare input and output, or reference and sample measurement. And then there are two ways, or more ways, but two common ways are the transmission diagram, which simply compares reference sample and sample, and gives you a transmission in percent, or an absorbance or extinction measurement, where you have it on a logarithmic scale. which especially makes sense when you have high differences in magnitudes, especially when watching like optical filters and so on and characterize them. Applications for this type of spectroscopy are, as mentioned before, optical filters, of course, and food and beverage quality control, like seen in the left bottom picture here. This is an example of coconut water, where you can see scattering and, of course, therefore related absorption in the measurement. The spectra on the right are concentration rows of coffee. Here in the scope mode, where you can see the original spectrum, and down here in transmission or absorption mode, where you can see the results and how they are shown there. Another point is definitely material analysis in the chemical and physical lab. This can also be a valuable technique when using other techniques like the following. The next type of spectroscopy is Raman spectroscopy. This has another physical background. It's described as inelastic scattering of light, and therefore it measures molecular vibrations and sometimes rotations. These vibrations and rotations provide a lot of structural information of the sample, especially in a chemical and physical way. It's a non-destructive technique, and one of the big advantages is there's nearly to no sample preparation required. A basic setup for Raman spectroscopy, very simple and easy to integrate in this point, consists of a powerful light source, preferably a laser, and additionally preferable with narrow line width. You need some kind of optical access to the sample, which could be a probe, like shown beside the laser housing here, and a cooled and high sensitivity spectrometer. Here you can see an example spectrum of polystyrene, which is a polymer and typically consists of a lot of molecules and even more atoms, of course. When you look at the graph, the x-axis scale here isn't shown in nanometers, but in some kind of inverse centimeters, which is called wave numbers. A specialty of Raman spectroscopy is that the wave numbers shown on the x-axis are relative to their excitation wavelengths. So on one side, you have great comparison to infrared spectra, which are also noted in wave numbers, but in this case they are absolute, which is a measure of energy. And the other point is that these relative wave numbers have the advantage that you can reproduce the position on the wave number scale with every excitation line, every excitation wavelength that you use. You don't depend on the color of the laser, simply said. Another very advantageous point is that a Raman spectrum has very few lines compared to other spectroscopic techniques, which make it very easy to analyze and good to use. You don't need to throw a bunch of chemometric algorithms on it to get some information out of it. So unless sometimes it's helpful, especially when you have greater compositions where this may make sense, but in general, these line-staffed spectra are very easy to evaluate. Just for a bit of conclusion, the advantages of Raman spectroscopy are that it's very easy to integrate and you get simple spectra. Easy to integrate because when you have the equipment, you only need some kind of optical access or an optical port to your sample. This can be just like a hole where maybe a probe fits in, or a lens or a microscope, whatever you need. But there are some disadvantages. Most of them it is possible to overcome. So one of the disadvantages, it has comparatively weak signals. What means weak signals? The Raman yield, spoken in that terms, is very low because the process is very weak and you need approximately 1 million of excitation photons to get one Raman photon out of your sample. But with today's cost-effective and powerful lasers, this is not a big deal anymore. Another point is Raman spectra often have a point with luminance background. As the signals are weak, as said before, some kind of luminance like fluorescence, phosphorescence, aggregate luminescence spectra can overlay the Raman signals, which is very, very bad when you want to get more information out of it. A bit of background is normally no problem, as the background signal is normally very broad compared to sharp Raman lines. Another point is when you want to do cost-effective Raman spectroscopy, is that compact spectrometers, due to their physical footprint and the dispersive possibilities of the gratings used inside of the spectrometers, is that they can cover only a limited wavelength range or wave number range. Normally for standard spectrometers, it's about from 2000 2200 wave numbers. But for at least the last 2 points, there are solutions. So first point, the background. There are two ways to overcome background distortion. The first one is move your excitation wavelength away from the visible spectrum to the NIR, but this has a few counterpoints. When moving the excitation to the NIR, your incident photons don't have enough energy to excite electronic transitions needed to excite fluorescence or something. But the two counterpoints are, one, the spectrometers, when you go to 1064 nanometers excitation, the spectrometers you normally use will be indium gallium arsenide spectrometers, which are something like double to triple the price of normal silicon spectrometers, silicon-based spectrometers that you can use in the visible range. Another disadvantage when shifting to the NIR with the excitation is that your weak signals are even weaker because the scattering efficiency in Raman goes down with the fourth power of excitation wavelength. So when you go longer with your excitation, the smaller your Raman signal gets. But therefore you can use more powerful lasers. The other point is to go right the other way around. When you move to the deep UV and, for example, excite with wavelength like 248 nanometers, which is very in deep UV, you can overcome the background problem by luminescence, as most autofluorescence background starts at approximately 270 to 300 nanometers. This has a great plus because your Raman spectrum, starting from, let's say, 200 wave numbers and going up to over 3000 wave numbers, stands totally alone, free from background fluorescence. And the other point is, if you want to measure luminescence or fluorescence spectra, These are not distorted by some maybe intense Raman peaks. And as I said before, the wavelength, the fourth power of the wavelength law is here valid too. But as we go into the blue, we'll gain a lot more of scattering efficiency in the deep UV. The second problem I mentioned before was the limited range of the spectrometers. There's a solution one can overcome with, and this takes advantage of the fact that we use a relative wave number scale related to the excitation wavelengths. So when you use, let's say, a laser for your Raman experiment with 785 nanometers excitation wavelength and have a spectrometer set accordingly to that range, you can get very close to the excitation wavelength and get a spectrum of the so-called fingerprint region. This contains information, a lot of structural information on the atomic or molecular structure. But in sometimes it's necessary to do more proper quantification or identification via the stretch region, where especially for polymers, where you can distinguish them. Or if you want to measure the water content, you won't get to this point with only this spectrometer unless you shift your excitation wavelength a bit down to the blue, just enough that you end up in the end of the fingerprint spectrum. So if you go down like about 1700, 1800 wave numbers from 785 nanometers, you will end up in something like 680 nanometers. And there, the difference, these excitation difference leads to the point that you get another Raman spectrum of the same sample that starts relative to your now shorter excitation wavelength farther away. So let's say exactly at the point where the other spectrum stopped. So now you have the second half of the spectrum, and you can see here like these stretch bands, and here these water bands. And this with only one spectrometer. The only point you have is you need proper optics to support both wavelengths, and a spectrometer or a spectrometer software where you can set the excitation wavelength accordingly so that it directly shifts the wave number scale to your two excitation wavelengths. Applications for Raman spectroscopy are manifold, like of course lab-related or production-related quality inspection, as well as hazardous materials, or sometimes even drug control, let's say on airports with some kind of handheld device. There are also sorting applications that rely on Raman spectroscopy, especially when you think of waste, of plastic waste. It's important to distinguish between all the types of plastic that are in your collected plastic waste, as not every type of plastic can be recycled the same way. If you can separate them from each other, you can get more and more effective in your recycling. You get a better recycling efficiency with less effort and less cost. Of course, then we have the medicine and pharmaceutical branch, where Raman spectroscopy is also used to see the drug distribution within a pill. So it makes sure when you have one of these pills that you can break apart in the middle, that you have the same concentration of the effective drug on both sides. Not that you take one half in the morning and get all the pharmaceutical effective drug, and on the other hand you have in the evening no effect anymore, because the second half only consists of the filling material like lactose and something else. And another point, and this is the most recent point, I think, is of course astronomical and extraterrestrial research, like shown here in the with the Perseverance rover, with the extended Sherlock arm on the bottom of the picture, which consists of a Raman spectroscopy and luminescence spectroscopy instrument to find traces of extraterrestrial life and check if Mars would may have been in a habitable way for humans in the past and maybe in the nearer future too. The last specific application I want to talk about today is light measurement, with the three big topics: colorimetry, radiometry, and photometry. So what can you measure when you measure light? So this can be intensity, it can be the color, and of course, therefore related, the color temperature, especially when thinking of displays, and flicker. When we go into lighting measurements, there are three types of measurement that one has to take apart from each other, more or less. This is radiometric measurement, which measures the light in, let's say, normal physical dimensions and normal physical units. Then you have the photometry, simplified said, which measures a bit the same, but the results are more referred to the human perception of light. And then there's this spectroradiometric measurements, which breaks it down to even more scientific or precise scale by measuring the light by each individual wavelength increment. Basic optical configurations for these measurements can be, of course, an integrating sphere, which you see in the top picture, that thing that looks a bit like a tiny robot, but of course, there's an integrating sphere where you can measure radiant power or the respective other physical dimensions, spectral radiant power or the luminous power. Then the cosine character, often used for irradiance or the related measurements, or the radiant intensity measurement. The irradiance is more based on an area, and the radiant intensity is referred to with a solid angle. And a lens when you want to measure the radiance or luminance respectively. Colorimetry. So there are two terms of colorimetry. The one is the chemical colorimetry that you can use to design nice-looking cocktails, or check in the beer production maybe if your beer color is too dark or too light. So, of course, for other purposes. And the other point of colorimetry is the color measurement reduced to the physiological color reception. Therefore, there are most oftenly used tri-stimulus adopted silicon detectors or spectrophotometers. So tri-stimulus adopted detectors normally are some kind of photodiodes or photodiode arrays equipped with filters that mimic the human eye's response with the photodetector to get an objective result in your measurement. Or spectrophotometer, where you will have to properly calibrate your spectrometer so that you will have the proper correction coefficients to assign the color measured to the color space you want to assign it to. Calibration is necessary for example, accurate reproduction in digital imaging and modern lighting solutions. As you can see with the sample picture below, this calibration, so these monitors aren't calibrated, or if they are calibrated, they're very bad. What you can see is you have a rather neutral one on the left, a very warm or yellowish one in the middle, and then a more I don't know if it's more blue or more red. Can't tell from here on the right side, but as everyone is working from home and maybe working with more than one monitor, this can be very annoying when always switching between these monitors, and every time the colors aren't reproduced the same way. As the last thing to say is that, of course, LEDs and solid-state lighting cover more and more the part that halogen lamps and fluorescent tubes had in the past. Therefore, it's definitely needed to measure brightness, color, and especially flicker to ensure high-end production quality, and don't make this light annoying by constantly flickering when switched on. And a big point at this way is, as the illuminated surfaces and displays are more and more common and get trend to be bigger and bigger, there's a trend to perform two-dimensional, so area measurements of large areas to perform a 100% quality control. As when you have to perform spot measurements on huge displays or so, you will have to take a lot of spots to ensure that the results are constant. So this was my last prepared slide. If you have any question, I hope a lot of questions have been posed in the meantime, and okay, now I will have the questions here too. So, what is the penetration depth of Raman spectroscopy? Yeah, this question is a bit related to the excitation wavelength you use. So in general, one says the redder, or so the more red the excitation wavelength is, the deeper can it go. It also depends on the optics you use. It can range from from a very tight focusing lens or microscope objective, where you can have it a small sample. When you go confocal, you can go nearly to a very, very thin disc. And of course, it depends on the sample, how good is the scattering, how strong is the back absorption of the sample. And yeah, when a transparent has a good scattering efficiency, and is also very very transparent, it's hard to discriminate the depth, how deep the excitation light or the collected Raman light comes from. Next, please. Could Raman spectroscopy be used on powders? What could be the sample's preparation and the precautions to take in this case? Okay, of course, Raman spectroscopy can be used on powders easily, as you may have seen in one of the sample. You can somehow use like a handheld device and just point it at a bag, at a plastic bag, and get directly information on that. So you can put it in a bag. You can put it on a microscopy slide. So the precautions to take into account every time you work may it be Raman spectroscopy or everywhere else you use an intensive light source or especially a laser, is that you have proper protection and laser safety precautions. So when using a handheld device or using it with a probe, always unless you have a certified laser safety concept or a sample holder with an internal trigger that only triggers the laser when the lid is fully closed, make sure that you have proper protection and yeah, to keep your eyes and your skin and your surroundings safe. Okay. This is a very fine question. I don't know if I have the correct answer on this, but let me read it out loud. So in absorption spectroscopy, how do you account or compensate for wavelength dependent and depth dependent scattering? As an example, the sun looks white at midday, but red in the evening, but the absorption spectrum of air should always be the same. Yes, this is an issue that's I think not really easy to discuss, but let me give it a try. So when the sun looks white at midday because it shines nearly vertically, let's say it this way, simplified, and especially when having the incident angle, you don't have that much difference between the air layers, and therefore not that much dispersion and yeah, and scattering issues. But when you go down to the evening, when you have the Earth here, you're pointed here, and the sun comes from here, you will have different ways through the atmosphere. Of course, the absorption spectrum of air should always be the same, but you have also terms, yeah, terms of dispersion, as you have different lengths for the light to travel at different angles. Yeah, the other point is you need to correct for let's say every daytime. So the absorption spectrum should be the same when you take a reference at every daytime you want to measure, and then you will have the same absorption spectrum. It's all about the reference in this case. I hope this is somehow correct and answers the question, but we can discuss this later, of course. Yeah. Okay, where can I get the data set of wave numbers for materials? For example, if I need the Raman wave number for gamma iron oxide. There are some databases that are, some are free, some are open access, some are commercial, and especially for something like minerals or so. One of the sites I would recommend for first research is rruf.info. So maybe we can put this somehow, or I will give you an email back. But rruf.info, they can give the give the chemical composition, and then you will normally get a lot of Raman spectrum. The other point is definitely scientific literature. There's also a lot of open access, and yeah, if Elsevier would more push open science, but this goes more political. They would widen up the access for the broad community. So scientific literature is always a good point, and otherwise try out rruff.info, rruff.info. Do we have another question? Then let me thank you for your attention, and let me hint you to our next webcast on 14th of April 2021. This is a webcast with our partner Ozela about advanced diode laser technology for industrial and mainstream 3D sensor applications. And we hope the best for all for safety, and we look forward to welcoming you again on April 14th, same time as today, 3 p.m. Central European Time. All the best, stay healthy, and goodbye. Thanks.